what they're interested in for the current weather and the forecast. So stay engaged, ask them questions, and take it away, Kari.
Hi. So first, let's take a brief overview of what's happening in general. So right now we are doing the infrared satellite image. So right now we are seeing here the Hurricane Epsilon that we're going to talk later on. And we have a small disturbance over here that I think that National Hurricane Center assigns like 20% of development in the next 24 hours, I think, or 72 hours. Here we see the effect of the front cycle the cold front that we are having experiencing for the last 24 hours, and the development that is moving into the mix into the east coast of the U.S. So now looking at another broad area of the. So this one just to show because I saw some interesting pictures on the internet about the fires in Colorado. So this is just showing the fires that were happening, I think, over here in this area. Okay, it's moving too fast. Yeah, over here, these fires are in there that we are seeing there. It was kind of impressive, smoke accumulation over that area. And so we look at different perspectives here. I think at the end of the loop, we're seeing a big yellow dot that is starting growing up, and this represents the fires that was happening over Colorado. And it was an impressive fires that was happening there. So moving now to look into the radar image. Yes. So we're seeing the rain band that was moving yesterday night until this morning over Madison, Wisconsin, over Wisconsin. And we see the extent of this rain band that is practically cover the vertical United States, starting from the Michigan all the way to Texas. And I was just looking at this scale yesterday, and this area over here in Texas was really small yesterday, but we're seeing the growing of this mesoscale, or a small scattered thunderstorm that was growing over here due to the effect of the frontal cyclones that we were experiencing in this moment. So now looking at the surface observations. So let's just start like 12 hours before, just to see the evolution of this front cycle in our area. So this is right now, we're seeing this kind of small, but we are seeing mostly overcast sky in the central and Midwest area, and pretty clear skies over the Florida and part of Texas and California. Small temperatures are pretty close to the dew point, so we have a high content of moisture over this area. And we have a warm advection. Winds are moving from the south in this part of the U.S., and we're having starting the development here of the cold front, where we have a cold advection that is moving south.
Can you zoom in on this for us, Kari? Because then we can see some of those temperatures. Maybe you had a plan to do that anyway, but I think you just click once and you get a zoomed in version.
Do we? Okay, no, that much better. Can you see much better?
Yeah.
Okay.
It's still going to be necessary if you want to draw our attention to temperature contrasts across this front to actually call out some of the numbers, because it's not really easy for an old person like me to see it from this far away, but it's a nice image.
I'm trying to zoom a little bit more, but okay. Okay. I think here we can see most the contrast and the wind direction that here mostly is coming from the south, and here we have wind direction from the north. how I just mentioning, here we have temperature pretty close to the dew point. Actually, right at 12 hours before, we really have 100% of relative humidity in that area. So we see the contrast in which direction that is marked. So it's showing the front line that is developing over that area. So something I'm missing. I think at some point Colorado right now it doesn't have it, but I think it was like 6 hours before that he had this weather symbol for the fires that was happening there, but I don't see it right now.
This is and this is from 12 hours ago, you said?
Yes.
I think. Yeah, so look at the Rockford temperature. Is that 69 at Rockford, just south of the Wisconsin-Illinois border? 69 over 61? Just to the west of Chicago.
Here.
Yeah. Is that 69 degrees? I can't read it.
Yeah, it's 69.
And look
69,
at
61.
45 at Madison, 24-degree temperature contrast across us. We were supposed to warm up yesterday afternoon, but I think the front always stayed south of us. We never got in the warm air.
No.
And yet there was plenty of it. Look at it, it's uniformly around 70, all the way from the Gulf Coast up to Detroit. Just unbelievable. We never saw that.
Yeah. So if we look at the curing conditions, the surface of the version, the curing conditions, oops, this is, okay. Much better. We can see the movement of this front side, the cold front. When we see in this here, we have the cold advection over here, and we have the warm advection. It's not that strong, but it's over here. We have warm advection moving here. So we clearly see that this front system is just moving to the east coast of the U.S. right here. We still have higher contents of moisture over the area, so that means that it contributes to the formation of precipitation in that region. And how we see actually since yesterday a lot of inches of rain. So right now, yeah, we can see the symbols of, I think, if I remember correctly, these are the symbols of smoky skies over Colorado. So that what we're seeing right now in the surface of the regions.
And I think if you can always go around and pick out a few stations and contrast them, like the one near the so-called Boot Heel of Missouri, Cape Girardeau, 82 over 68 along the Mississippi River, and then south of Columbia, 42 over 39. So there's a 40-degree temperature contrast across maybe 120 miles in southeast Missouri, and the same is true from St. Louis down to wherever that is. It's not Carbondale, but someplace down in southern Illinois, 34 degrees. Yeah. Extraordinary temperature contrast, and then 57 near Champaign, 78 just across the border in Terre Haute. Unbelievable. It's a classic cold front.
Yes. So now looking at the large scale of the upper levels, we're gonna look 12 hours before first, just to see the evolution again. So we are seeing up to 15 millibars of the millibars. So we are seeing the high speed and the height and temperature contrast here. So I can say correctly, this is the polar jet that is moving over our area. And here, as we discussed in class, we have the entrance of the jet here. And when we have the change in speed and the strophic wind speed here, we have a change in that. So that means that we're going to have the strophic wind just pointing in that direction, and that means that we're going to have a convergence over this area. So that means that we're going to have circular motion here, and we're going to have rising motion over here. So that practically is where we can say for now for what's happening with the jets over the area that we are actually having the front cycles moving to.
What other characteristic of the flow would promote divergence in roughly the same area at upper levels. So you talked about the along flow speed change in the jet entrance region. Is there anything else in the tri-state area, Iowa, Wisconsin, southeast Minnesota, that might contribute to upward vertical motion?
Well, we have, you say in this area too?
Yeah, right in there. What about the curvature of the flow? That's also going to induce agiostrophy, right? Because you got to round the bend of the flow along the Missouri River there on the Iowa-Nebraska border. And so if you're turning the direction there, that requires an acceleration, and the acceleration produces some agiostrophy that's divergent downstream of the upper trough. So you have two things working in the same direction over parts of our state, maybe the northern part of the state at 12Z this morning more than over us. And I think that's where there was snow, actually.
Yeah, it was snowing in the Dakotas actually yesterday.
Yeah.
They have a really high amount of accumulation of snow. Or I don't remember the amount, but maybe between 2 inches. So now just looking at the evolution of the jet. So
Can I say something?
Yeah.
yes.
That the divergence in rising motion here yesterday, that was the biggest rain of the year.
Yeah.
I had 3.37 inches.
Oh, did you really? I wondered if you'd get more than 2.
And I saw up by Baraboo, there was up to 8 inches.
Wow. That was amazing.
It's just under 2 at the airport,
Yeah.
like 1.88.
Yeah, so, I mean, one of the things that's part of the story here is the high dew points to the south, which were over us, or at least in the middle troposphere yesterday, a lot of water vapor in the middle troposphere. But then the other thing is what's forcing the air to rise. And so you're kind of going after some of that, so.
I think it's really unusual to have this much precipitation without some kind of a tropical thing going on. I don't recall a regular baroclinic system like this producing this much precipitation over us. This is unusual.
It was strong forcing in a number of different ways, but you're right, the moisture part of it is maybe a little bit uncharacteristic of its divorce from the tropics, yeah.
Yeah, so here right now, the curing condition of the polar jets, we see just a slightly movement of the polar, so it's a little more to the north in this area, but it's not really a big change. It keeps seeing the different speeds over the entrance of the jet stream, and also has Joe mentioned the change in speed direction that also contribute to the hysterotrophic winds over that area.
Which area at this time? This is a prior time too, so you want to make sure you tell us what time you're showing
Yeah,
us.
so,
This is from last night.
No, this one is right now, like the 0 UTC.
0Z 23rd.
Yeah.
Yeah, that'd be last night.
That's last night. 12Z 23rd was this morning. So you went backwards in time here.
So yeah, so that was happening when the front was moving over our area actually.
Okay, that's what you want to show. Okay, I get it.
Yeah.
Make sure your audience gets it. You got to tell them that.
Okay. Now, looking at 5 millibars, we are gonna use. Again, to see the evolution, we're gonna go 12 hours, 12 hours back in time, just to see how these events evolve. We're seeing that where we have here, we have a rise here, and we have a trough over here. So we are seeing the downstroke of the downstroke of the trough. That is moving over the Midwest and Midwest area and the West area. So here we have the hurricanes actually that have a really nice shape. So looking to the map from last night. So let's just take that one. We're seeing a little bit of intensification of this trough. So that means that we're gonna have, we have a surface lobe over this area. So that will contribute to the formation of rising motion over there. This is what we were experiencing yesterday. Okay, so if we look at the surface level, the equivalent potential temperature first. 12 hours before, so we practically didn't see, we still see a transition. We have a warm cold belt that is moving northward, and a cold belt that is moving southward. So we have higher theta E. We actually have theta E showing in the map right now. So when we have higher theta E, that means we have higher content of moisture. And then when we see it, we don't have really a strong evolution here or strong cold fronts happening. But when we just look at the map 12 hour, from last night, so we are seeing like more strong gradient in temperature over here. So we're seeing that we have a northward movement of the warm air over here and moisture is moving over the area. And we have a cold air and dry air moving to the south over this area. So this contrast in temperature and moisture is what was contributing actually to the development of precipitation that we were experiencing yesterday.
How does it do that?
Night.
How does it do that?
Can you repeat?
Yes, how does it do that? What does it, what's acting upon this temperature contrast to turn it into a precipitation producing engine?
Because we are having here, since we have warm air moving there, right? So we're gonna have rising motion, and we're gonna have a diabatic cooling, a diabatic expansion.
So it's just the warm air advection that forces the air to rise?
Can you repeat that, sir?
Yeah, is it just the warm air advection that forces the air to rise? Is that what the argument is?
Right
Anybody
now,
else in 751 can help.
I will say that this is a sample of the thermal adiabatic circulation.
That's true, but what forces that circulation? That's what I'm asking. Anybody, please. You've been dancing around it, Kari. It's frontogenesis, right? There's this substantial contrast in temperature. We can't really see the wind vectors there, but I've seen them in close up on some other diagrams. It's clear that the winds are acting to compact that horizontal temperature contrast, and there's no way in the middle latitudes when that happens that you don't spur a secondary circulation that's thermally direct. So that's what's causing that relationship.
Okay.
So I want you to, when you're talking about the various elements on the map, that's a part of the discussion. The other part is making the diagnosis. What is it that's physically making this happen? So you want to add that for sure.
So now looking at the same level, but looking at the precipitation temperature contrast. Here in the same location the way we have the gradient in temperature in theta E, we also have the accumulation or precipitation over the area. That was this from last night, so this is the higher amount of precipitation that we're falling over it, at least for Wisconsin. So, yeah. We will now look at the Q-mega equation. Yes. So I'm gonna do 12 hours again, and then the one from last night. The yellow represents the vertical motion. The blue represents the sinking motion. So we have a vertical motion happening in the downstream of the trough over there. So the two things that are contributing over there is the one is the temperature gradient, and the other one the increase in hysterotrophic vorticity in the column above the surface lobe over this region. So these two things are contributing to the vertical motion over this area. So when if we go back actually to the other map, this one. One thing that we can say here is that the Q vector will be pointing, will be conversion or pointing in this direction, so we will have conversion of the Q vector over here. So that means that we have upward motion here, and we will have divergence of the Q vector over this area. And we will have sinking motion over there.
Now, how do you know that from just this map? Do you have you thought about what the Q vectors would look like on this map, or are you just saying upstream and downstream of the trough there's ascent and descent?
Because yesterday we were discussing that the Q vector is moving across the the gradient temperature. So when we see these, we're gonna see that it's the gradient of, the vector, the Q vector, will be crossing these lines over here, and will be converging over this area.
I see. Okay, so but that's from a genetical process, not really related to the upper wave.
Yeah.
Okay.
So yeah, I think I'm ready to move to the searching. So you.
Alright, so, can you guys hear me?
Yeah.
Okay. So I'm going to start off I always like to start off my math discussions by looking at the large scale pattern. So I have the AO index above, so the black line is what has already happened, the red lines are the different ensemble members, and then we can see we have the 7-day forecast, the 10-day forecast, and the 14-day forecast, and this is the AO index at 1,000 millibars.
What model is doing these forecasts?
Sorry, the NSEP.
Oh, okay.
So what I want to look at is we kind of are experiencing a pattern change. So like for the past maybe week or so, we've been consistently in like a negative AO pattern. And I'm going to show that a little bit later. We can see the blocking high over Greenland, which is indicative of this. And then I'm also going to show the NAO index as well. So we can see kind of those patterns in the past. And then as we go through the forecast, I'm going to just focus on the 7-day forecast since the 10-day and the 14 has a lot of spread, and I don't really feel like this is a confident forecast. So the yellow kind of highlighted part is the one standard deviation of the ensemble members. I guess that's like a blue line is the ensemble mean, and the two red lines are the range. So the upper one is the upper level range of the ensemble members, and the bottom one is the lower level. And to me, for the 7-day forecast, I think we can positively say with some confidence that we're going to have a regime shift into a positive AO pattern, which will be important into the forecast.
Chelsea, can you put this in perspective for somebody like me? Does this normally happen, where you're going along at about a 0 Atlantic Oscillation Index until about mid to late August. Let's say mid-August to be safe on this diagram. And then suddenly it starts to get more variable. Is that a function of the time of year as much as it is this particular year, or is there, so what's the background climate of that? Do you know?
I don't specifically have a climatology, but in general, in the winter, during the winter season, there's more variability, just because there's a starker temperature gradient. So we have like the cold polar air and then the really warm tropical air. And what a negative AO signal pretty much is saying is that the pattern is very wavy, which is what we usually experience in the winter, at least in the northern hemisphere.
And that's wavy in the Atlantic Basin, right?
So
Or is it a hemispheric signal?
it's kind of a hemispheric signal, but like more specifically, I guess the NAO is a part of the AO index, which specifically looks at the Greenlandic and Icelandic low and high pressures.
Yeah.
So, but the AO is, I guess, the more bigger picture than the NAO.
Oh,
So
it
this
is,
is
okay.
showing like more of waviness across the hemisphere, and then the NAO index is specifically looking at the Greenlandic area.
Okay, thanks.
But usually when you see a negative AO, you see a negative NAO. So they're very closely linked. And I just want to show that right here, just to prove it to you guys. The NAO is doing a little like weird kink in the first couple days, but generally in the 7-day forecast it's trending towards, I would say positive, but I would argue it's kind of straddling the neutrality line. So not a super strong signal, but when I show it in the maps, you can really see the transition between the negative NAO to the positive NAO, and the same with the AO index. And this is the same information from the AO, but just the 500 millibar NAO index. So before I move on to that, this is Alicia Bentley's page, and we are at a negative 108 hours. This is 18Z Sunday, October 18th. And I just want to kind of walk through the pattern here. So we've seen like this kind of high pressure building over Greenland, which is the negative AO, negative NAO signal. And more specifically tied to the NAO signal, we have this lower pressure in the Atlantic Basin that kind of extends over into Europe, but really straddles the Atlantic Basin. And what this is kind of doing is forcing, because it is a Greenlandic block, and that's why last week we've really had the cold air pull down into Wisconsin, because we're forcing that ridging over the northeast United States, and that trough was really digging. And as we go through time, we can kind of start to see the regime shift, where the Greenlandic high is starting to clear out, and we start to build in lower pressure as we go into the forecast. So this is the 0-hour forecast, and this is for 6Z today. So we can see how that pattern kind of has changed for us. Maybe not over the Midwest, but specifically over in this region where we have the transition of that high Greenlandic pressure to more low in the Icelandic Greenland area. And we're starting to build higher pressure into the Atlantic. And of course we have Hurricane Epsilon, which I'm not gonna really discuss today since there's a lot of other things too.
Although I will say, at 4 days, Epsilon turns into the biggest cyclone I've seen in the Greenland Sea in a couple of years minimum, and it really revs up a positive NAO.
Yeah, I was really tempted to talk about it, but I was trying to focus in on the Wisconsin, so I don't
That's
stray too far. But yeah, you can see the jet stream really picks up Epsilon as we go through time and really shears it apart. And as you said, intensifies into a low, and that's going to impact like England and I guess Northern Europe.
Yeah, it's the strongest storm in the Western Hemisphere this year by the time it gets done 4 days from now, including all the hurricanes.
I mean, especially with all the moisture it's pumping into it and the dynamic forcings. So now I'm going to go into the forecast region. I'm going to try to make this a little bigger. Okay, so what we're looking at is the NSEP ensemble for the 500 millibar height. And what we can see is that red line is going to be the 5,820 meter height, and then the blue line is the 5,640 meter height. And I guess in this like yellowish color is going to be the ensemble mean for both of those height lines respectively. And as we can see, this is for 0Z Thursday. So I guess we're a little bit back in time. We can see that everything is pretty I guess there's a clear pattern, and I'm going to talk about the possible omega block that this is. I'll show later in the forecast. I'm not sure if I can confidently say that's a true omega block, but I think it resembles a lot of the pattern that an omega block has. So I'm going to just jump this through time. So now we are at 0Z Saturday, October 24th. And we can see that we still have what resembles an omega block and kind of like a wide, maybe deep trough through the Midwest. And all the ensemble members are pretty tightly close to each other, so I would say this is a pretty confident forecast. And we're only, I think this is a little behind, but this is a 48-hour forecast, so that's not surprising to me. So as we keep moving forward, we see what is maybe the omega block starts to break off, and we really see ridge building over the Alaska area, which I'm going to go into later. And another feature that I'm going to also talk about soon is this positively tilted trough that's kind of going over the Midwest to the western United States, and how that might play a role into our weather. So I'm just going to keep advancing this. We see that our ensemble spread starts to get a little greater, so our confidence in the forecast is getting a little lower, which is what we expect when we go forward in time. But I also would like to point out that we have a pretty high confidence in over the Pacific Basin, where all the ensembles are pretty much converging on the solution of a pretty straight jet over there. And things are kind of getting messy over the Eastern Pacific and North America. And this is the next time. It's starting to get really messy, and I think what the models are having trouble doing is kind of picking up what is happening to the omega block feature, and also what's happening with the positively tilted trough. It looks like some ensemble members are keeping the trough intact, and it looks like others are making it cut off into a low that will eventually track in through the southern United States.
Yeah, Chelsea, you just said, now we're at 6 days here, right?
Yep.
And you said what the models may be doing. So are we trying to diagnose the model, or are we trying to diagnose nature, or can you do both at the same time? So is there something systematic about these flows that would lead to the downstream confusion in a forecast versus is it just the model?
I'm not sure if I completely understand what you're asking.
That's because I didn't articulate it well, but you know, one can look at these. These are great. I'm glad you're showing these and marching through them systematically like this. One can, upon seeing such things, wonder what's wrong with the model that it can't lock in on some of these features that, you know, like the omega block feature that you're talking about, and now it's a companion block and cutoff over the Southwest, whereas other parts of the hemisphere it looks pretty locked in. So that's a physical question, or I mean a model question. And then related perhaps is a physical question. Is it systematically more or less likely physically that in certain regimes, or the exit region of the Pacific Jet, which is past the date line in this case, that you have this really confused pattern downstream? So I guess that's a physical question, not so much a modeling question.
But like you said, I agree. I think it's kind of a two-part question, but I also think that they tie kind of together since we use the models to forecast, and what physical nature wants to do is influencing what the different ensemble members with the different initial conditions want to do.
Yeah.
So I think, in my opinion, it could be wrong. I think what's giving the models trouble is just the omega block in general, because as we look in through, I'm going to show the height anomalies next, but it doesn't really stay that long as a typical omega block would. Sometimes we see them for, stationed over for a week, Maybe on the rare occasion, a week and a half, 2 weeks. But this is kind of a feature that's maybe 2 days. And it's not completely strong. And I think this positively tilted trough is giving some issues. Whether or not this low is going to cut off or not, or continue propagating.
Yeah, okay, and then a thing about blocks, which I don't know that much about, but this one doesn't look like it penetrates that far poleward. And as that shrinks its overall wavelength, makes it smaller, and so maybe it's more transient just because of that is one factor. Is that possible?
Yeah, I was going to show a deprog DT on Alicia Bentley's page in a little bit, but what it looked like to me, and I guess I'll talk about it in more detail, is that there's kind of a low pressure system that's originating from the Pacific that's propagating this way, and it kind of plays 2 roles. I'll save that for when I show the actual map.
Okay.
But the placement of that low seems to indicate whether, I guess, how flat the ridge is,
Okay.
or how strong it can build.
Mm-hmm.
So I think there's a lot of different factors playing in,
Okay.
and there's a lot of different solutions based on where these lows and high pressures are actually going to be. Yep.
I think this is very interesting, by the way. I'm very excited about this talk of yours here. This, I think, is the classic problem with chaos theory for a hemisphere, the blocking patterns. They represent these stable equilibriums that are very difficult to predict when they're going to break down and go to another equilibrium. So the fact you're showing this with the ensemble really brings that home, how you're in a stable equilibrium in other places, but right there it's the models are having trouble picking that up because just small details can throw it to a different solution entirely. And this is the classic problem of chaos. This is why we do ensembles, to alert us to these breakdowns that are trying to occur that we really can't resolve because in chaos a little tiny difference can make a huge difference. And that's where it's very sensitive right there because of that.
Yeah, and that's interesting because, when you look at a hemispheric map, you have simultaneously, you have regions that are well resolved at 6 days. You don't really have much of a question about what's happening off the west coast of Africa, for instance, at 500 millibars. That's pretty well resolved in the middle Atlantic. Same with south of Kamchatka in the central Pacific. But in the boundaries around those regions, like you're saying, little things can screw it up in that jet exit region in the Pacific that'll just throw the whole forecast into chaos downstream. I'm interested in the physical side of that, but there's equal interest that could be had for the modeling side of that. Is there a way to smooth some of those features out and reduce the spread at our current physical knowledge? And that's a whole other can of worms, which is really interesting.
Yeah, no, I completely agree with sorry.
I just have a basic question. What is an omega block?
So an omega block, sorry, I probably should have explained this. So a canonical omega block is pretty much, and this can be anywhere in the world, it just happens to be right here, is typically a large ridge, and on either side of the omega block is usually, I've only seen it with like 2 cutoff lows, so you'll have a cutoff low here and a cutoff low to the east side as well. So they call it an omega block just because it looks like a capital omega. And stuff like this in the Brex blocks, I think, like Greg mentioned, is really important for longer term forecasts because it kind of gives us an idea of the general circulation and the general pattern that we can kind of rely on a little bit more than a really super wavy pattern with a lot of ensemble spray. Any other questions before I move on from this? Okay, so this is again Alicia Bentley's map, and this is the 500 geopotential height anomalies, and this is for the GFS model. And as I showed before, we're starting to get into the positive AO pattern, with the low over Greenland, Iceland area, and the high building into the Atlantic. So as we go forward in time, we see that the low pressures are continually building into the Greenland area, and once epsilon moves off into the northern Europe, we kind of get a more concrete, broad Atlantic high, which I think this is more of a canonical positive NAO pattern. So I'm going to just step back again at hour 0. And now I want to focus on the ridging over Alaska. So as you can see, we have 2 lows that are essentially pretty much cut off, and we have this really large ridge. And this is the low I was talking about earlier, which I think is going to play a role in how large this ridge can build, because it seems like in some cases this low really wants to come in and squish that ridge down. But I think there's a lot of forcing that can help with the ridge building. So I'm going to keep moving forward in time, and we see that the ridge is kind of deepening as we get a pretty deep positively tilted trough here and a really deep trough here, and I think that's a really anomalous low. It's maybe 3 or 4 standard deviations from normal, which is pretty significant, and the ridge is maybe about 2.5 standard deviations above normal. So this is a really significant feature that's going to impact the forecast. And when I was looking at this earlier, like a couple days ago, this positively tilted feature wasn't too prevalent, and we actually really dug in a deep trough. So it looks like this general pattern is going to play a large role in the general United States pattern that we're going to see throughout the forecast. So some of my hypotheses for why this ridge is going to build is we have a really large component of meridional wind in the ridge, and what that's going to do is we have lower values of the Coriolis near the equator and higher in the poles. So this is going to do 2 things. It's going to affect anticyclonic planetary vorticity northward into the ridge, more on the western side. So I think maybe part of the reason why we're seeing some of the ridge broadening is we're getting a little bit of the anticyclonic vorticity advection on the west side, as well as downstream from the ridge, which is what we typically see. And that really strong meridional part of the wind is going to do 2 things. It's going to bring in a lot of warm temperature advection. We have warm tropical air down here, and we're forcing that to come upwards. And what I'm going to show also is we have a lot of moisture being funneled into this into this ridge, for 2 reasons. And I'm going to switch to that so we can talk about the moisture transport.
Is there a strong surface cyclone downstream? You're probably going to tell me. Is there a strong surface cyclone downstream of this anomalous trough that's in the Central Pacific?
So in the Central Pacific?
Yeah, the one that's upstream of the ridge that you're talking about.
Yeah, so I can show a surface map in a little bit.
Okay.
But I can't remember how low it was, but there was a pretty strong low kind of right in this region.
Yeah, because I think you're making some good points. If I had to make a guess, I'd guess that low PV air, which is warm and moist from low latitudes, is probably a bigger contributor to the ridge building than the planetary vorticity advection, only because there's such a strong upstream low.
Yeah.
And it probably also because the wavelength of this feature is probably not quite large enough for the planetary vorticity to be the major contributor, but that's a guess.
No, I completely agree. I think it's more of a, like you said, a minor constituent, but I think it's something that can't be ignored.
No, if you're pushing in the same direction, you want to mention it, definitely.
Yeah. So this should, yep, and this is at hour 06Z Friday. This is also Alicia Bentley's map. So this is integrated vapor transport, which is shaded, and the vector is obviously the vector arrows. And what we see in this ridge area, so remember we have the ridge kind of over this Alaska region. This is part of the low pressure that developed from that really deep trough in the Pacific.
Oh, so this is from the same time, Chelsea?
Yep, sorry,
oh, okay,
0.
Okay, yeah, okay, I see.
This is just at a lower level, the 700 height, and before we were at 500.
Okay.
So we can really see a really deep low pressure. And I think these are working together constructively, because we're having our cyclonic flow here, and then we have a high pressure here, and they're both kind of, I guess, sucking in all the moisture from the tropics and we can see we have like a long kind of train of IVT, and that's gonna lead to latent heat release if it's convecting or creating clouds, which is going to just buff up that ridge because of the latent heat. And as we go forward in time, we see that this IVT really strengthens with the low and the high pressure working together. We're really funneling up that tropical air. And this is 54 hours in, 12Z Sunday. And we just see this IVT transport is just getting much greater. And as we go into the forecast, that moisture is, I really think is going to help buff up that ridge and then provide ingredients for weather later down in the line. I also have another hypothesis for the ridge building over the Alaska region. So let me refresh this since this is from the 21st.
Can I just make a comment on your last evolution that you showed, those several maps? It seems to me that the trough to the west and the cyclone to the west get weaker, which is curious, and the ridge is resilient and seemingly immovable. It's at 140 degrees west. The combination of those circumstances leads, I think, to a fairly substantial moisture plume, as you point out, but it doesn't get far north because the ridge maintains the anticyclonic curvature right there in the northern Gulf of Alaska, and it can't get further north into the state of Alaska or the western part of Canada. Consequently, the ridge can't grow meridionally.
Yeah,
And that might be one of the factors for not only influencing our weather, because it will produce upper troughs in the northwesterly flow, but it doesn't really block the flow quite the way that it could.
Yeah, I completely agree. And like you said with this low, how it's weakening, you'll see it more clearly in the deep prog BT, but earlier forecasts, we're forecasting this low, I believe, to be stronger, and we saw like that response in the ridge where it started flattening a lot. And then the more recent model runs, the low is kind of similar to what we see now, where it's a little weak and we don't really see the dampening of the ridge as much. So this is just a hypothesis. I'm not sure how to quantify this. Maybe with new Era 5 data, we can look more at fluxes. But this is the global daily sea surface temperature anomaly, and it's clear that this whole like Gulf of Alaska region, Bering Sea, and along the Pacific, Eastern Pacific, we have really warm temperature anomalies, and I hypothesize that these might play a role in latent heat release for the ridge to build. I'm not sure how significant of a contributor that would be, but I don't think it's something to ignore because of those fluxes from ocean to the atmosphere. I'm not sure if anybody knows more about that than me. Yeah.
Well, one thing you can look at is the equivalent potential temperature of where the moisture is, because the air really can't get any higher than the equivalent potential temperature in terms of the potential temperature. So usually when you get up to the northern part of that area, the ridge at high levels, when you're looking up, if you're looking up at 200 millibars or so, you're talking about a ridge up at 350, 360 equivalent potential temperature. That air can only get up there in the tropics. There's really nothing you can do in the Atlantic, no matter how moist it is, to push that air up that high. You can warm the lower levels a little bit, but I think when you're looking at these ridges, that's up very high.
Yeah, I agree, and I think this is a good example of how the mid-latitudes and the tropics can kind of really work together, or not work together.
I'm just kind of glancing at this, and I don't have any real good current maps, but I suspect a lot of this forcing is coming from the maritime continent, and there seems to be a lot of convection going on there that's really building a lot of potential energy up high, and I think that's what's feeding this ridge. But
Yeah, I think that's a good point. I think the MJO right now is in phase 5, so right past the maritime continent, so that might have some sort of influence. I'm not sure how significant or if it would be deconstructive or constructive, but I think that would have been an interesting thing to look at. I was going to talk about it later in terms of the TCs. Yeah?
Yeah, to go along with that, the MJO has been pretty strong.
Yeah.
It's like the 15th, so the past few days. So that might be contributing to
Yeah, I completely agree. I think it has some sort of influence, and I think if I had time to go deeper in it, I think it would be an interesting thing to explore. I think we're getting a little low on time,
Yeah, we're about 10 minutes shy
so
of the end.
I think I'm going to switch to the tropics because I think there's going to be some interesting things happening with the hurricanes. I didn't plan to talk about Epsilon, but I was talking about maybe the potential for tropical disturbance in the Caribbean. So I guess this is a theme. I like to just look at the large scale circulations, what's going on seasonally and in the large scale. So this is the model predictions for ENSO, and this is valid for October 2020. As you can see through July, August, and September, that first stuff, and the September, we've been in a steady La Nina, and we're confidently can say we're gonna stay in La Nina for the rest of the winter season. In the red line, we have the dynamical average, so that's the average of all the dynamical models. And in the green line is the average for all the statistical models. And it seems like, besides maybe a few outliers, all the ensemble members have us sticking with La Nina for the rest of the season. And for the consequences for this hurricane season, I can't find an updated one to current October, but this is the wind anomalies at 250 millibars for the month of September. And as you can see, we just have anomalous easterlies in the tropical region and in the Caribbean. And as we know with the thermal wind, we can assume this is going to decrease the seasonal and overall shear, which is very conducive for tropical cyclone development. So now we're going to look at the MJO real quick, and I'll kind of speed through this because I want to get to more of the meat of the discussion. But this is the MJO phase diagram and for the RMM, and here is the NSEP model. And there's different models from America that we have here, the different versions of NSEP. And generally, the American models are just having a propagation eastward, although the yellow lines are the ensembles. It's kind of going a little crazy, but this is what we kind of generally see in our MJO forecast, on like really major ensemble spreads. And interestingly, this is for the ECMF, and all the European models are having the MJO do this weird kind of stationary westward propagation until it propagates eastward, but it also has it propagating eastward more weakly than the American models. And the reason why I want to show this is I think the MJO is going to be pretty important for NETC development. So this is, I believe, Carl Schreck's page from NC State, and this is Chi, which is the velocity potential at 200 millibars, and this is for the CFS forecast. So for those who aren't familiar with velocity potential, we can kind of think of this green, the negative anomalies as large-scale divergence, and the positive anomalies as large-scale convergence that's associated with the MJO. And as we can see, the MJO has really spawned off a lot of hurricanes and TCs in the past. And we can see that a lot of them are associated with the MJO passing, as well as Kelvin waves, which are outlined in the blue. The main reason this is because these waves are bringing anomalous moisture and upward vertical motion in the regions they pass through. So it's typical, if the conditions are right, for tropical storms to develop off of these waves. So there's two things I want to mention. So we have Hurricane Epsilon here, and we see that this is right off a Kelvin wave, but I'm not sure if I can confidently say that the Kelvin wave was the trigger for this, just because Epsilon is higher north, and the Kelvin wave we typically see really close to the equator. So I think it's important to look further into this. I'm not completely sure, but we see these solid black outlines outline the propagation of the MJO, and we see that typical eastward propagation, and this is kind of in the region of North America. So when this wave passes through, there's a possibility, although it's kind of a low possibility, of a disturbance to occur in the Caribbean. This is the National Hurricane Center outlook, and although they have a less than 40% chance of development, I think it's still important to really look at what is going on and why or why not this might develop. I think for reasons that I'll explain in a little bit, it's probably not likely, and I agree with the National Hurricane Center. So if you look in the area of the Caribbean, this is the ocean heat content. For those who aren't familiar, this pretty much just shows where the deep, warm water is. And for a TC to develop, you need really deep and warm water because it's gonna upwell the water from deeper into the ocean. And this is really gonna help fuel a hurricane. But I think what might be an issue is the shearing. So this is the 500 to 850 millibar vertical shear vectors. And this is from the GFS and valid 12Z October yesterday. So let me refresh this. Oh. All right. Well, I guess this is the latest one, so I'll just walk through this. So the
Chelsea, you only got about 2 minutes.
Okay, sorry. The higher values here show more shearing. So the higher the shear vector, the more likely any TC development or convection is just going to be pretty much sheared away and not able to develop. And if we focus in on the Caribbean region, we see that it's in that white and dark blue fill, so not as much shear. But if this were to propagate northward, it's going to go into an area of higher shear in the Gulf of Mexico and the Eastern Atlantic. So I guess I'll stop there so I don't go over time.
Well, give us the punchline. So what do you think is going to happen to that disturbance? What's your thought?
So I think the ingredients are there, but I think there's more things to look at. There's a possibility of the Central American gyre to be a significant feature. I personally have not seen a strong indication of that in the forecast, but I know it's been a topic of subject which can help, spawn up a convective area that can spin into a TC. And I think because of the anomalous warm waters, the La Nina condition is reducing overall shear, and then I think really the big trigger is going to be that MJO passing through. So I think if the shear ends up staying pretty low, I think there's a possibility of something forming, but I don't think anything significant.
I guess the most recent tropical weather outlook has it up to a 70% chance of development now.
Okay.
Okay, any final comments or questions?
Somebody online had asked about whether the potential vorticity being pushed up towards the pole might have anything to do in the uncertainty of forecasting that Pacific ridge.
I don't know how to answer
Yeah,
that question,
Yeah, I think it would.
but I don't know what the question means.
Well, the question means that if you have very low potential vorticity, you have very low inertial stability. And predictability goes hand in hand with inertial stability, because inertial stability means that slow manifold quasi-geostrophic dynamics tend to govern. But when you throw these low potential vorticity anomalies up there, you ruin that. And you're not so governed by quasi-geostrophic, and then it becomes more unpredictable.
But the ridge never really made much northward penetration. Didn't even get north of the Gulf of Alaska. So, but maybe that's far enough north to make
Well, that's
to
pretty far,
wreak
yeah.
some havoc, I guess. Yeah. Okay. Well, thank you very much for your discussion today and everybody's attention. Pete, thank you. We'll reconvene next Friday.